Engineering applications. Combustion is applied in many cases where energy is needed in the form of heat or work. Combustion, energy in work, heat. We use a natural gas stove, water heater or furnace, or a propane burner for a soldering, or the picnic grill, to mention a few domestic applications with combustion that utilize the heat. Lawn mowers, snow blowers, backup power generators, cars, and motorboats are all domestic applications where the work term is the primary output driven by a combustion process using gasoline or diesel oil as the fuel. On a larger scale, newer power plants use natural gas in a gas turbine, and older plants use oil or coal as the primary fuel in the boiler. Steam generator, jet engine, and rocket use combustion to generate high-speed flows for the motion of airplane or rocket. Most of the heat engine described in Chapter 7 and with simple model as cycle in Chapter 11 and 12 have the high temperature heat transfer generated from a combustion process. It is thus not a heat transfer but an energy conversion process, changing from the reactant to the much higher temperature products of combustion. For the Rankine and the Stirling cycle, the combustion is external to the cycle, whereas in the internal combustion engines, as in the gasoline and diesel engine, combustion takes place in the working substance of the cycle. In external combustion, the products deliver energy to the cycle by heat transfer, which cools the product, so it is never a constant temperature source of energy. The combustion takes place in a steady flow arrangement with the careful monitoring of the air-fuel mixture, including safety and pollution control aspects. In internal combustion, the Brayton cycle, as the model of gas turbine, is a steady flow arrangement, and the gasoline-diesel engines are piston-cylinder engines with intermittent combustion. The latter process is somewhat difficult to control as it involves a transient process. A number of different parameters can be defined for evaluating the performance of an actual combustion process, depending on the nature of the process and the system considering. In the combustion chamber of gas turbine, for example, the objective is to raise the temperature of products to a given temperature. If we had a combustion process that achieved complete combustion and that was adiabatic, the temperature of the product would be the adiabatic flame temperature. Let us designate the fuel-air ratio needed to reach a given temperature under this condition as the ideal fuel-air ratio. In the actual combustion chamber, the combustion will be incomplete to some extent, and there will be some heat transfer to the surrounding. Therefore, more fuel will be required to reach the given temperature, and this will be designated as the actual fuel-air ratio. The combustion efficiency at a combustion is defined as combustion efficiency eta combustion, fuel air ratio ideal, and fuel air ratio actual. On the other hand, in the furnace of a steam generator, the purpose is to transfer the maximum possible amount of heat to the steam. In practice, the efficiency of a steam generator is defined as the ratio of the heat transferred to the steam to the higher heating value of the fuel. For a cool, this is the heating value as measured in a bomb calorimeter, which is the constant volume heating value, and it corresponds to the internal energy of combustion. We observe a minor inconsistency since the boiler involves a flow process and the change in enthalpy is the significant factor. In most cases, however, the error thus introduced is less than the experimental error involved in measuring the heating value, and the efficiency of a steam generator is defined as eta steam generator heat transfers to steam per kilogram fuel and a higher heating value of the higher heating value of the fuel. Often the combustion of a fuel uses atmospheric air as the oxidizer, in which case the reactants also hold some water vapor. Assuming we know the humidity ratio for the moist air omega, we would like to know the composition of air per mole of oxygen. One mole oxygen plus X mole water. Since the humidity ratio omega mv on ma, the number of mole of water is mv equals to mv on or equals to omega ma on mv ma on mv, and the number of mole of dry air per mole of oxygen, the number of mole of dry air per mole of oxygen. X NB on N oxygen M air on M vapor humidity ratio. This amount of water is found in the products together with the water produced by the oxidation of the hydrogen in the fuel. In an internal combustion engine, the purpose is to do work. The logical ways to evaluate the performance of an internal combustion engine would be to compare the actual work done to the maximum work that would be done by a reversible change of state from the reactants to the products. This, as we noted previously, is called the second law efficiency. In practice, however, the efficiency of an internal combustion engine is defined as the ratio of the actual work to the negative of the enthalpy of combustion of the fuel. This ratio is usually called the thermal efficiency for the internal combustion engine. Thermal value minus HRP0 heating value. This equation is applied. The same scaling for the work and heating value must be used. So if the heating value is per kilogram fuel, then the work is per kilogram of fuel. For the work and heat transfer in the cycle analysis, we use the specific values as per kilogram of the working substance, where for constant pressure combustion we have HP equals to HR plus QH. Since the heating value is per kilogram fuel and QH is per kilogram mixture, we can write the relation M total M fuel plus M air M fuel mass, and thus QH HV AF mass plus 1, where a scaling of HV and AF on a mass basis must be used. The overall efficiency of a gas turbine or steam power plant is defined in the same way. It should be pointed out that in an internal combustion engine or fuel-burning steam power plant, the fact that the combustion is itself irreversible is a significant factor in the relatively low thermal efficiency of these devices. One other factor should be pointed out regarding efficiency. We have noted that the enthalpy of combustion of hydrocarbon fuel varies considerably with the phase of the water in the products, which leads to the concept of higher and lower heating value. Therefore, when we consider the thermal efficiency of an engine, the heating value used to determine this efficiency must be borne in mind. Two engines made by different manufacturers may have identical performance, but if one manufacturer bases his or her efficiency on the higher heating value and the other on the lower heating value, the latter will be able to claim a higher thermal efficiency. This claim is not significant, of course, as the performance is the same. This would be revealed by consideration of how the efficiency was defined. The whole matter of efficiency of devices that undergo combustion process is treated in detail in the textbooks dealing with that particular application. Our discussion is intended only as an introduction to the subject. Two examples are given in the related videos. The next section is the summary of the chapter.